Well, well, well. Another stream of learning Rust. So, let's start by doing a bunch of shit that I could be doing off stream, but since, there is some sort of time that needs to pass before anyone joins the stream, I might as well do it on stream, right? And the terminal as well, we bloop bloop. That should be it. Let's go to Regel and follow this link. So, yesterday's stream. Hey, Mood! I actually didn't read anything offline, so we're going to be continuing from the same point that we left at yesterday. So let's go. Dangling references. In languages with pointers, it's easy to erroneously, once again, what a word, create a dangling pointer, a pointer that references a location. I'm sorry, but I really want to stream. So welcome. I just checked and mood isn't taken, which is surprising. Yeah, that is. I feel like that should have been taken, or period isn't a valid character. No, I think it is a valid character. Just two in a row aren't. Or maybe I'm talking about Twitter in this case. I think that's valid because the dot is one of the best characters to, like, not make it obvious that you couldn't just take mood. It's pretty good. I actually, one time, I wanted to create a Twitch account, so I tried to make it, put in my nickname, Axel Fulbler, and it's taken. I'm like, well, goddamn. Thought that it was taken by a really old account of mine, which I didn't even try to get access to, so I put Axel Fulbler _, and that worked. But then I ended up just getting access to the old account, so now I'm just Axel Fulbler. On the very rare occasions where I do use Twitch. I don't stream there though, simply because all my audience is on YouTube, and moving first of all myself and also them, like all of you, to Twitch seems like too much of a hassle. Doesn't seem too worth it so far. How do you come up with this name? Good question. So, my previous nickname before Axel Fulbler was Quack High, spelled like this, I think, and it worked in the same way. I just sat around and I just launch different letters together until they sound good together. Quack High has high, which is kind of a word, and I didn't really like it, so I wanted to change it to something better. So I just started jumbling random characters together and came up with Axel Fulbler. Not a single pair of characters or more makes any sense in that nickname, until it was pointed out to me that Axel actually means a thing. I was like, ah. But it's obscure enough where, for the most part, the nickname means nothing, and that is the exact intention. And that's exactly why, if you search for my nickname, you will only see me. Since it's so hyper-specific, it's only ever going to be me. Me over here sweating for a good name, so true. Mine is probably not gonna be taken by anyone else. I doubt that it could be a coincidence, and I hope there's no one, like, evil enough to grab my nickname because it's mine. I doubt that will happen, so yeah, that's another nice thing about having a specific username. If it's something not that specific, somebody can like think of someone else as if they're you, because the nickname is like similar. I doubt there's anything similar enough to Axel Flobler, so I'm pretty safe when compared to something Destroyer 112. All right. Yes, a dangling pointer, a pointer that references a location in memory that may have been given to someone else. By freeing some memory while preserving a pointer to that memory. Oh, by freeing some memory while preserving a pointer to that memory. Oh no. In Rust, by contrast, the compiler guarantees that references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. Please don't! Don't! So, in other words, in Rust you can be sure that will ensure that the data will not go out of scope before the reference to the data does. So the data will only be cleared if the pointer is as well. Nobody really popular has the name Mood. It's just a tiny dedicated amount of people who steal it a bunch. Yeah. And even so, you are going like through a problem trying to get the correct one. Where now I recognize what a stupid fucking decision Discord is making. But yeah, just jumble random words together, or rather random characters, and then you'll never have that issue. But also, people will have no fucking idea how to pronounce your username correctly. Understandably enough, but oh well, that's the trade-off. Ensure the data, yes. Let's try to create a dangling reference to see how Rust prevents them with a compile time error. So, reference to nothing, dangle returns a reference to a string. Expected named lifetime parameter. Ooh, that's where lifetimes come into play. I mean, to be more fair, I feel like this shouldn't be a reference to begin with, and you should instead like return the actual value. But once again, it's just an example. Trust me, it could be much worse. I have some priority, and it's not a popular name. Like I literally have to think of everything possible because just how many people use this. Discord. Yeah, I guess. Fuck. I never liked the 4-number system. But compared to now, everyone will have to fucking come up with some complicated way to just have their username. That's kind of shitty. When something like Twitter or Instagram or literally any other place, like there, to begin with, you had to use a special username, which is not the case for Discord. For the longest time, you could pick your own username that you wanted. And just removing it because reasons that are not very good. So expected named lifetime parameter, which we'll get to, I imagine. This function's return type contains a borrowed value, but there is no value for for it to be borrowed from. Consider using the static lifetime. Ah, that's interesting. So, since this value of s is dropped on scope end, the reference doesn't reference anything because the data it's referencing died. Oh, and also underscore mood isn't taken, but I'm not even gonna bother. That would be stolen. Well, Ed, I feel like special characters before the username is not very attractive, but maybe it is. I find it interesting that in Rust, for labels and now supposedly lifetimes, you use a single quote, a single quote before the word, and you'd like, that's so like strange. Such a strange character to pick. Why not the @ symbol, for example? I feel like that would work better, since what are the @ symbol even used for? Not much. At least I can't think of anything. For more information about this error, blah blah blah. This error message refers to a feature we haven't covered yet, lifetimes. We'll discuss lifetimes in detail in chapter 10, but if you disregard the parts about lifetimes, the message does contain the key to why this code is a problem. This function's return type contains a borrowed value, but there is no value for it to be borrowed from. So exactly from this, I came to a simple conclusion. Let's see if I'm correct. Let's take a closer look at exactly what's happening at each stage of our dangle code. So dangle returns a reference to a string. S is a new string. We return a reference to the string S. Here, S goes out of scope and is dropped. Its memory goes away. Yeah, that's exactly what I think was happening. That's interesting. But at that point, once again, why are you returning a reference? Just return the value, no? I feel like, yeah, surely. Because S is created inside dangle, when the code of dangle is finished, S will be deallocated. But we try to return a reference to it. That means this reference would be pointing to an invalid string. That's no good. Rust won't let us do this. The solution here is to return this string directly. Yeah, that's what I thought. This works without any problems. Ownership is moved out and nothing is deallocated. That feels a bit weird, like here we just created a problem for ourselves that wouldn't actually happen, and that's how you fix it, by not making that problem to begin with. You're welcome. Like, well, no, it's not necessarily obvious, it's just that I wouldn't return a reference from a function. At least I can't imagine a situation where I would. The rules of references. Let's recap what we've discussed about references. At any given time, you can have either one mutable reference or any number of immutable references. References must always be valid. That's another guarantee. References are always valid. So many nice guarantees. Next, we'll look at different kinds of reference. Slices. The slice type. Slices let you reference a contiguous. What is contiguous? Please let me know. Contiguous. Sharing a common border, touching. Next or together in sequence. Okay, I see. Sure. Lets you reference a contiguous sequence of elements in a collection rather than the whole collection. Oh, so it's like a range, kinda. I see. A slice is kind of a reference, so it does not have ownership. Important to know. Here's a small programming problem. Write a function that takes a string of words, separated by spaces, and returns the first word it finds in that string. If the function doesn't find a space in the string, the whole string must be one word, so the entire string should be returned. Okay, that's interesting how it's going to be done in Rust. let's work through how we'd write the signature of this function without using slices to understand the problem that slices will solve. So we pass a reference, an immutable reference, by the way, of string that returns question mark. We'll get to it, I guess. The first word function has a string reference as a parameter. We don't want ownership, so this is fine. But what should we return? Good question. We don't really have a way to talk about part of a string. However, we can return the index of the end of the word, indicated by a space. Let's try that. So we return usize because, once again, the length method, which, oh my god, the 3 letters. We couldn't survive if we had to type those in because, yeah, because that's exactly what modern programmers do. We type in the full name of every function, which is why it should be length and instead of length, and it should be rev instead of reverse. Because why make it more readable? I guess that's so far my only complaint with Rust. It has unnecessary shorter names, just unnecessary. Like, what are you saving on? Fucking bytes of the document? Be real. Like, a Rust program is probably longer than other languages to begin with. So, no, you're not saving shit on that. So, we pass that same string reference. Bytes. So we call the method as bytes on the string that we passed and get bytes. What does that mean? I'm not sure. But bytes we can now call. Oh my, tractor again. I'm telling you, this is the reoccurring character on the stream. Why does he just keep coming back? Okay, bytes, we get an iterator and we enumerate from it. So that's how you do index in a for loop using a tuple. So for index and a reference of an item, if item is binary space, interestingly, I think that's binary. Maybe not. But yeah, just putting a letter before a string to mean something feels weird to me, instead of like using an actual character. We return that index. We return that index, but if there's no such thing as a space in that string, we just return the length of the string. Interesting, because we need to go through the string element, to the string element by element, and check whether a value is a space will convert our string to an array of bytes. Using the asBytes method. Surely there's something easier than this though, right? Something like string split, like HK has. Surely like something this simple is not this hard. Just unnecessary, I feel like. So we get bytes as bytes. Next, we create an iterator over the array of bytes using the iter method. Once again, like, you could make it not just iter, but like iterator or get iterator and so on. Like, what are you saving characters for? We'll discuss iterators in more detail in chapter 13. For now, know that iter is a method that returns each element in a collection, and that enumerate wraps the result of iter and returns each element as part of a tuple instead. The first element of the tuple returned from enumerate is the index, and the second element is the reference to the element. I kind of like the shortened method / function names. I kinda don't. I don't know, like, I'm so used to IntelliSense that if I actually still typed in anything by myself, then yeah, cool, but at this point I don't think it's necessary. Because having expectable names let a new programmer, like, use the language easier, because they can often just guess what it is. So say you want to get the length of a string in a new language that you haven't yet used, what you're probably going to check, like, is just using the length method on the string. And if that doesn't work in that language, then you Google. Like, why add that step? Just make the default length method, just as literally everyone expects. It's strange. This is a bit more convenient than calculating the index ourselves, true. Because the enumerate method returns a tuple, we can use patterns to destructure that tuple. We'll be discussing patterns more in chapter 6. In the for loop, we specify a pattern that has I for the index in the tuple and item, a reference to it, for the single byte in that tuple, because we get a reference to the element from iter enumerate. We use the ampersand in the pattern. Inside the for loop, we search for the byte that represents the space by using a byte literal syntax. If we find a space, we return the position. Otherwise, we return the length of the string by using slang. I've never seen a byte literal before. I sure hope that there is a more, I guess, reasonable way of doing this kind of task. But we'll see, I guess. We now have a way to find out the index of the end of the first word in the string. But there's a problem. We're returning a usize on its own, and it's only a meaningful number in the context of the string reference. In other words, because it's a separate value from the string, there's no guarantee that it will still be valid in the future. Consider the program in listing 48 that uses the first word function from listing 47. So we create a mutable now, string. We pass it into the first word function, and now we have the length of the first word. I'm so sorry for all these tractors. So now we have the length of it in a variable, but if we empty it, now we can't trust word. Yeah. This program compiles without any errors, and it would also do so if we used word after calling sClear, because a word isn't connected to the state of s at all. Word still contains the value 5. We could use that value 5 with the variable s to try to extract the first word out, but this would be a bug because the contents of s have changed since we saved 5 in word. Having to worry about the index in Word getting out of sync with the data in S is tedious and error-prone. Yeah, managing these indices is even more brittle if we write a second word function. Oh, Jesus Christ. Its signature would have to look like this. Yeah. Now we get 2 indexes. Now we're tracking a starting and an ending index. And we have even more values that were calculated from data in a particular state, but aren't tied to that state at all. We have 3 unrelated variables floating around that need to be kept in sync. I've never thought about it in this kind of sense. The unrelated variables floating around that need to be kept up in sync. Yeah, that is hella annoying now that I look at it. Luckily, Rust has a solution to this problem: string slices. specifically string slices? Can I slice anything else? A string slice is a reference to part of a string and it looks like this. So a range, kinda. That's cool. Rather than a reference to the entire string, hello is a reference to a portion of the string. Specified in the extra range bit. We create slices using a range within brackets by specifying starting index, ... ending index, where starting index is the first position in the slice, and ending index is one more than the last position in the slice. Not sure why they do it that way. I guess because everyone expects it to be that way. Usually, ranges are exclusive, which I never really quite got. But alright then. Internally, the slice data structure stores the starting position and the length of the slice, which corresponds to ending index minus starting index. So, in the case of let word, this entire thing, world would be a slice that contains a pointer to the byte at index 6 of s with a length value of 5. A pointer to the byte at index 6 of s with a length value of 5. That's interesting. So I think it actually points, yes, it points to the same place in memory on the heap. That's interesting, meaning if we break the initial string, we also break this thing, which is what is supposed to happen, or rather should happen. With Rust's double dot range syntax, if you want to start at index 0, you can drop the value before the two periods. In other words, these are equal. Yep, that's nice. By the same token, if your slice includes the last byte of the string, you can drop the trailing number. That means these are equal. I never understood why ranges in so many languages are end exclusive. I know, right? In Kotlin they are inclusive. That's what you expect, right? Like, why is suddenly that number not included, even though I typed it in? And then you have to do like something like length +1. Where is that +1 coming from? Oh, because they're exclusive. Like, sure, an experienced programmer will immediately want to check that, but why isn't it done in the obvious inclusive way? That's so strange. Includes both 0 and 5, but less than 5, that amazing syntax. I love that decision of less than, which, like, we're so used to meaning exclusive when we compare numbers, so that's a very nice syntax. So yeah, like, why isn't it the case like everywhere? Maybe I'm missing some important context for why this spread out to such an extent, but this is so weird. By the same token, if your slice includes the last byte of the string, right. So yeah, you don't have to specify the last one if it goes to the end. Yeah, like I don't understand that decision. Maybe it's like matters a lot somehow, and more like low-level stuff. I don't know. You can also draw both values to take a slice of the entire now that's interesting. What? So you specify a slice of the whole thing. What's the use of that? I guess we'll know. String slice range indices must occur at valid UTF-8 character boundaries. If you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. That's interesting. So if you try to cut it, it's like, say you have a string with some Unicode emoji. So this, I think, no, wait, this, yeah, here we go. So this character contains 3 characters actually. First of all, the non-gendered shrug emoji, then the zero width joiner, and then the female sign emoji. And when they're sent all at once, it becomes, in most places, the full emoji that is actually multi-byte. So I guess if you try to cut it inside, you'll get an error, which is cool. I didn't expect that. For the purposes of introducing string slices, we're assuming SC only in this section. A more thorough discussion of UTF-8 handling is in the Storing UTF-8 Encoded Text with Strings section of Chapter 8. With all this information in mind, let's rewrite first word to return a slice. The type that signifies string slice is written as a reference to string. And that's a bit confusing, to be fair. That's a bit confusing. Like, we already have reference to a string, and then you would think, oh, reference to string also, but now it's lowercase and it's just str, and oh right, it means string slice. Unsure of this decision. The type that, yeah. So now it will return from 0 to the current index, which is nice to begin with, because we actually get the string slice that we can then use, I imagine, which by itself is a reference. Well, the emoji example is kind of wrong. Oh, really? It is valid to stop a slice in between those 3 characters, but not within the characters. Well, hold up. How do you even do that at all? How do you cut inside of a character? Like, you put, instead of an integer, a float? That's ridiculous. Huh? Even just the emoji itself is 2 or 3 bytes long, and splitting inside of is invalid. Oh. Huh. That's interesting. That's good to know. Huh. Yeah, and otherwise we just return the slice of an entire string, which is once again strange as fuck, but sure. We get the index. The discrepancy comes from what a character is considered to be. Yeah. A character can be a different amount of bytes. But I guess you don't really think about it that often, because you don't really have to consider it in normal situations, where here it matters. Most languages will just say that one character is 1 byte, and that's not always true in UTF-8. I see, yeah. Interesting. Huh. That's one new thing that I'll have to consider. Oh, the tractor is red now. Different color. If I understand this correctly, you could just drop 0. And I'll probably always do that when, like, I'm starting from the beginning, or when I'm always slicing to the end. I would even argue that it's more readable to omit those characters that don't make a difference in this case. Now, when we call first word, we get back a single value that is tied to the underlying data. The value is made up of a reference to the starting point of the slice and the number of elements in the slice. Hold up, I think I might have a better understanding for why it does it that way. So let's say we have string. Imagine that this is just text, this is not particularly code. So string, what if we start at index 2? Well, let's imagine we're not using HK, so we start at this. And now 6. So we start at 2, so here, until the 6th character. In Rust, excluding that one. 6 minus 2 is 4, so 1, 2, 3, and supposedly 4. So my idea of why that is the case is wrong. I thought that, oh, maybe the second one doesn't store the index, but instead stores the length starting from the starting index, which is the reason why it's exclusive by default. No, turns out it is just kind of stupid, because if it was 4, it would be 1, 2, 3, 4. The fourth character is excluded. So I'm beyond surprised for why languages do it that way. Like, that is strange. That is straight up strange. Returning a slice would also work for a second word function. Yeah, and it's nicer that way. We now have a straightforward API that's much harder to mess up because the compiler will ensure the references into the string will remain valid. Remember the bug in the program in listing 48 when we got the index to the end of the first word but then cleared the string so our index was invalid. That code was logically incorrect, but didn't show any immediate errors. The syntax you write uses start index and exclusive end index. Yes, that's exactly what I expected at first, but then I thought I was wrong, because no way it's that stupid without a reason, right? So I thought that I was wrong for thinking this is the case. So I tried checking the logic behind that. No, I was correct. It is just kind of stupid, but the data structure that stores the slice stores the start index and the length. Yeah, I thought that those two were connected. Turns out no. That's how I understand it. Yeah, me too. I just kind of expected or wanted it to be a bit smarter. Well, I'm not a language designer, but like, sometimes in language design, maybe you have to take some trade-offs, but I don't see how making an exclusive thing is easier. Which would make sense because the end index must always be bigger than the start index, so why not just subtract the start from the end to get the length? Yeah, but that's the thing. If we go back to the example, if we subtract 6 and 2, we get 4, so we would expect it to have 4 characters. No, it has 3. So that was my idea of why it works that way, but it's not really a good explanation because we expect the length of 4, which is not the case. We don't get the last character. It's exclusive. So the length is 3. So the math you would have to do is the end index minus start index and then -1, which is just kind of weird. Like, if 6, or rather if the end index was inclusive, then yeah, we just 6 minus 2, we get 4, and that is correct. We get the length of 4, that is correct. We don't have to subtract 1 or anything, and like, here we go. But that's not what's happening. So, like, I wonder why. Do you? Keep in mind, the 2 here is supposed to be this. I know, like, I'm in an HK file, but let's imagine the indexes are 0 indexed. So 2, 3, 4, 5. Oh, my bad. My bad, yeah. No, both of us are. No, hold up. So let's start. 0, 1, 2, we start. 3, 4, 5, and 6 is exclusive, but yeah, we do indeed get the full length. So you're correct. You're correct. Yeah, that's my bad. So if we replace it with 5, now the length is 3, so 2, 3, 4, 5, but this is excluded, and this is the length. Okay, now it makes sense. What is even happening? I'm like half paying attention. We're trying to understand why the fuck ranges are exclusive by default. And now it makes more sense. Because yes, indeed, by subtracting start index from the end index, you get the length. You do. But if it was inclusive, you would have to remove 1. And I guess that matters. Maybe. So, good to know. I guess that's the reason. We figured it out. Still, like, I think it's nicer to use if it's inclusive. More clear and obvious. Even if most languages use exclusive ranges. Just kind of strange. Right. Remember the bug? Yes, we do. Not really. Yes, so the problems would show up later if we kept trying to use the first word index with an emptied string. Slices make this bug impossible, and let us know we have a problem with our code much sooner. Using the slice version of first word will throw a compile time error. Cool tip, use the console to set the video player's playback speed to about 105 so YouTube keeps the video quite updated without changing the sound too much. That's interesting. Huh. That's really cool. Good job. That's a very nice solution. Wow. That's cool. But also, how the fuck do you do that? So, we get a mutable string, we get the first word, which is now a string slice, and since we try to clear it, it actually says, what the fuck are you doing? Like, why do you take this thing if you're gonna make it invalid? Very nice. It's something that you would have to actively think about in another language, but in Rust, there are tools for you to more easily prevent all kinds of bugs. It's more annoying, I guess, in some sort of senses, because it's more strict, but in the long run, it's so worth it. With AHK, one of my most used hotkeys is the one that reloads my script, because shit can just break suddenly and for not understandable reasons, because of edge cases that I didn't even think about. In Rust, if I have those edge cases, it's more likely that first of all, I'm going to take care of them immediately, and second of all, that I won't be able to compile if those are still there. So that's very hope-inducing. Okay, so cannot borrow S because it also, yeah. That's cool. Recall from the borrowing rules that we have an immutable reference to something, we cannot also take a mutable reference. Because the clear needs to truncate the string, it needs to get a mutable reference. The print line after the call to clear uses the reference in Word, so the immutable reference must still be active at that point. Rust disallows the mutable reference in clear, and the immutable reference in Word. I'm brain rotting, and also my cat is meowing, and that always like throws me off balance. Like, stop. So Rust disallows the mutable reference in clear. Jesus Christ, hold up. Stop, stop meow, stop meow, stop. Зачем ты мяукаешь? Okay, I fed them, so I hope they're gonna chill out. Okay, so Rust disallows the mutable reference. So reference this. So, oh, this is an immutable borrow, meaning a reference. Cat. In clear, so this, and the immutable reference in Word from existing at the same time, and compilation fails. Not only has Rust made our API easier to use, but it has also eliminated an entire class of errors at compile time. Yeah, that's cool. I imagine like reading all this, you know the theory, but when you start actually doing things in practice, you'll have to rethink how you do things. And that's going to be very new and refreshing. String literals as slices. Recall that we talked about string literals being stored inside the binary. Now that we know about slices, we can properly understand string literals. The type of S here is so these are string slices to begin with. It's a slice pointing to that specific point of the binary. This is also why string literals are immutable. String slice is an immutable reference. Interesting to know. String slices as parameters. Knowing that you can take slices of literals and string values leads us to one more improvement on first word, and that's its signature. A more experienced rustacean would write the signature shown in listing 4.9 instead, because it allows us to use the same function on both string values and string slice values. Oh, yeah, that's true. If we have a string slice, we can pass that directly, but if we have a string, we can pass a slice of the string or a reference to the string. This flexibility takes advantage of derif coercions, a feature we'll cover in implicit derif coercions with functions and methods in chapter 15. Defining a function to take a string slice instead of a reference to a string makes our API more general and useful without losing any functionality. So we create a string, we pass an unfull slice, we pass the full slice, and we can even just pass a reference to it and it will act as a slice. Huh. Interesting. Huh. So now we have a string literal, which is actually a string slice. And the same thing applies. But when we pass it like itself, we can actually move the ownership into the function, which we can't do. We have to use a reference with the actual string type. I've never really needed to think that much about strings in my life. Other slices. String slices, as you might imagine, are specific to strings. Yeah, I'm so interested though. There are slices, okay. Are specific to strings, but there's a more general slice type too. Consider this array, just as we might... Interesting that it calls this thing slices and not like a range. But I think I've seen ranges be used in a different way, which is why these are not called ranges, because because that's not really what they are. God, I love my window manager. Like, just with a simple hotkey, I can fix a random change of the window that I just made. Like, It's very simple. It's not programmed in any kind of like smart way, but in a very predictable, bugless, I would say, way, where you just, let me actually show it. Manager. Of course you failed. Why wouldn't you? Yeah, basically we have a bunch of variables that I set, and then there are like a billion functions here. Oh, right. A billion functions here that just use these variables. And true, I could make a way for combining those variables into the eventual result instead of having all of these functions. But it's much easier to like bug-proof this entire thing by just having specific functions that are specific splits and so on. And I actually recently implemented new two functions. So Windows I and then D, and then this we do E. So now there is a 70-30 split, while all of that is a 70-30 split, but vertically. So my chat is here, but I can still do this. It's unlikely that I will want to that often, but it's very cool that I can, you know? I find that very nice to use, but what's even better is the fact that I won't have to on Linux, because there's just a window manager that I'm going to be able to use instead of programming my own, because Windows is so shit. Not giving me really any way to do this kind of thing with Windows with my keyboard, only having to use the mouse and some limited Windows arrows action. So that's why I implemented, and I quite like it, but Linux is going to be better. Right, so just as we might want to refer to a part of the string, we might want to refer to a part of an array. We do it like this. So yeah, so slices are always references. That's important to know, I think. Yeah. From 1 to 3, excluding, so starting from 2 and ending at 4, confusingly. Right? Hold up. 2, 3. Yes. Hold up. So 0, 1, 2, 3, excluding this. Oh, so we're just taking the first one. So 2 and 3. We'll take 2 and 3. See, that's why, like, exclusivity is hard to figure out. Maybe not hard to figure out, but more confusing that inclusivity would be, I feel like. Or even if instead of the ending index, you specify the length, like yourself. What do you think about that? Like, instead of 3, we would specify 2, for example, to mean check this one and another one, so the length of 2. Would that be easier to use / more understandable? My immediate thought is no, because if you have to change the first thing, you also have to change the second thing, and if you forget to do that, well, fuck. When in an index system, that's not really going to happen. At least not as much. But I don't know, maybe it would be nicer. It depends on the application, I guess. Part of an array, we do so like this. This slice has the type of slice of integer 32. It works the same way as string slices do, by storing a reference to the first element and a length. You'll use this kind of slice for all sorts of other collections. We'll discuss these collections in detail when we talk about vectors in chapter 8. The concepts of ownership, borrowing, and slices ensure memory safety in Rust programs at compile time. The Rust language gives you control over your memory usage in the same way as other systems programming languages, but having the power of data automatically clean up that data, but having the owner of data automatically clean up that data when the owner goes out of scope means you don't have to write and debug extra code to get this control. Ownership affects how lots of other parts of Rust work, so we'll talk about these concepts further throughout the rest of the book. Let's move on to chapter 5 and look at the grouping pieces of data together in a struct. Ooh. So I heard it's kinda like a class in terms of in Rust. Using structs to structure related data. A struct or structure is a custom data type that lets you package together and name multiple related values that make up a meaningful group. If you're familiar with an object-oriented language, a struct is like an object's data attributes. In this chapter, we'll compare and contrast tuples with structs to build on what you already know and demonstrate when structs are a better way to group data. We'll demonstrate how to define and instantiate structs. We'll discuss how to define associated functions, especially the kind of associated functions called methods, to specify behavior associated with a struct type. Structs and enums, discussed in chapter 6, are the building blocks for creating new types in your program's domain to take full advantage of Rust compile time type checking. Defining and instantiating structs. Structs are similar to tuples, discussed in the tuple type. The tuple type. Oh, that shit sounds funny. The tuple type section, in that both hold multiple related values. Like tuples, the pieces of a struct can be different types. Unlike with tuples, in a struct you'll name each piece of data so it's clear what the values mean. Adding these names means that structs are more flexible than tuples. You don't have to rely on the order of the data to specify or access the values of an instance. Oh, true. To define a struct, we enter the keyword struct and name the entire struct. A struct's name should describe the significance of the pieces of data being grouped together. Then, instead of curly brackets, we define the names and types of the pieces of data, which we call fields. What I'm not sure I like is the fact that, well, the syntax. First of all, the string literal without quotes and the commas, like, is that necessary? I don't know. We define the names and types of the pieces of data, which we call fields. Stores information about a user account. To use a struct after we've defined it, we create an instance of that struct by specifying concrete values for each of the fields. We create an instance by stating the name of the struct and then add curly brackets containing key value pairs. Fuck yeah, I love it. So there is an instantiator built in. We don't have to specify the fields in the same order in which we declared them in the struct. In other words, the struct definition is like a general template for the type, and instances fill in that template. And instances fill in that template with particular data to create values of the type. For example, we can declare a particular user as shown in listing 5.2. So that's pretty simple and reasonable. To get a specific value from a struct, we use dot notation. For example, to access this user's email address, we use user1.email. If the instance is mutable, wait, does a mutable instance mean you can't change the object? That's not what I fucking wanted to do. God damn. I did that. I pressed it by accident. Right, so does that mean this object is immutable, or this object plus its data is immutable? Let's see. If the instance is immutable, we can change the value by using the dot notation and assigning into a particular field. Wow, so the data is immutable as well. How to change the value in the email field of a mutable user instance. Fuck, we also have this guarantee too. That's great. Not that the entire instance must be mutable. Rust doesn't allow us to mark only certain fields as mutable. That's kind of unfortunate. As with any expression, we can construct a new instance of the struct as the last expression in the function body to implicitly return that new instance. So that's how we create builders. Shows a build user function. I literally just mentioned it. The amount of times I call out something and then the book literally mentions it in the next sentence, it has been so many times already. That returns a user instance with a given email and username. The active field gets the value of true. And blah blah blah. And we just immediately return it and just specify the struct's name to mean that, yeah. Cool. So we specify them and like boop. That's cool. It makes sense to name the function parameters with the same name as the struct fields, but having to repeat the email and username field names and variables is a bit tedious. Oh my god, what is it going to introduce? If the struct had more fields, repeating each name would get even more annoying. Luckily, there's a convenient shorthand. They didn't have to do that, but so cool. Using the field init shorthand. Oh my god, because the parameter names and the struct field names are exactly the same, we can use the field init shorthand syntax to rewrite build user so it behaves exactly the same but doesn't have the repetition of username and email, meaning we don't have to specify the value if that value is the same name as the parameter. Basically, it's being assigned automatically, and that is so incredibly cool. I kinda wish, though, that since a struct has to have every field immediately filled in with data, how about we don't even have to specify these at all because they are implicitly specified? That would be even cooler. Here we're creating a new instance of the user struct which has a field named email. We want to set the email field's value to the value in the email parameter of the build user function. Because the email field and the email parameter have the same name, we only need to write email rather than email. God damn, how many emails were here? A couple for sure, at least 7. Creating instances from other instances with struct update syntax. Ooh. It's often useful to create a new instance of a struct that includes most of the values from another instance but changes some. You can do this using struct update syntax. First, we show how to create a new user instance in user2 regularly without the update syntax. Oh, I see. We set a new value for email, but otherwise use the same values from user1 that we created in listing 5.2. Yeah, that's how you would imagine you would have to do it. Using struct update syntax, we can achieve the same effect with less code. The syntax, again double dots, specifies that the remaining fields not explicitly set should have the same value as the fields in the given instance. Oh, interesting. We kind of like expand user1 into everything else here. That's cool. That's nice. The code in listing 5.7 also creates an instance in user2. It has a different value for email, but has the same values for the username, active, and sign-in fields from user1. The user1 must come last to specify that any remaining fields should get their values from the corresponding fields in user1, but we can choose to specify values for as many fields as we want in any order, regardless of the order of the fields in the struct's definition. Note that the struct update syntax uses equal sign like an assignment. This is because it moves the data, just as we saw in the this section. In this example, we can no longer use user1 as a whole after creating user2. That I didn't expect for some reason, because the string in the username field of user1 was moved into user2. If we had given user2 new string values for both email and username, and thus only used the active and sign-in count values from user1, then user1 would still be valid. Because we used a compound value. After creating user2, both active and sign-in count are types that implement the copy trait, so the behavior we discussed in the stack-only data copy section would apply. That is quite interesting. Using tuple structs without named fields to create different types. Okay. I immediately love this so much. Rust also supports structs that look similar to tuples, called tuple structs. Wow, so creative. Tuple structs have the added meaning that the struct name provides, but don't have names associated with their fields. Rather, they just have the types of the fields. Tuple structs are useful when you want to give the whole tuple a name and make the tuple a different type from other tuples. And when naming each field, as in a regular struct, would be verbose or redundant. To define a tuple struct, start with the struct keyword and the struct name followed by the types in the tuple. For example, here we define and use the two tuple structs called color and point. That's pretty nice. Note that the black and origin values are different types because they're instances of different tuple structs. Yes, each struct we define is its own type. Even though the fields within the struct might have the same types. For example, a function that takes a parameter of type color cannot take a point as an argument, even though both types are made up of 3 integer 32 values. Otherwise, tuple struct instances are similar to tuples in that you can destructure them into their individual pieces. That's cool. So you can use a dot followed by the index to access an individual value. Yeah, so the whole point of this is making types so you can be more explicit in what your functions expect. So I love that. Unit-like structs without any fields. What? Why? We can also define structs that don't have any fields. These are called unit-like structs because they behave similarly to an empty tuple, the unit type that we mentioned in the tuple type section. Unit-like structs can be useful when you need to implement a trait on some type but don't have any data that you want to store in the type itself. So that will help us implement traits somehow. We'll discuss traits in chapter 10. Here's an example of declaring and instantiating a unit struct named always_equal. To define always_equal, we use the struct keyword, the name we want, and then a semicolon. No need for curly brackets or parentheses. Then we can get an instance of always_equal and the subject variable in a similar way, using the name that we defined without any curly brackets or parentheses. Working on the command palette. Good job, because that is one project and a half. Me, on the other way, I don't have anything to do aside from learning Rust and doing my course. That's the 2 things that I do every day, the last 2 I think days, and also watching Hunter x Hunter. So the 3 things. So no worries. To define always_equal, yes. Imagine that later we'll implement behavior for this type such that every instance of always_equal is always equal to every instance of any other type. What? Is always equal to every instance of any other type, perhaps to have a known result for testing purposes. We wouldn't need any data to implement that behavior. Oh, so it's like a special value? Not quite getting this. We wouldn't need any data to implement that behavior. how to define traits and implement them on any type, including unit-like structs. So I'm currently at a point where I'm starting to not understand stuff, but this is exactly where read twice comes in. After I'm done reading the book for the first time, I'll go in to reread it, and now I'll understand basic concepts even better because I have the context of later stuff that I can understand more, plus I'll be able to practice stuff and I'll know what to look out for. So yeah, that's quite interesting. Ownership of struct data. In the user struct definition of there, we use the owned string type rather than the string slice type. This is a deliberate choice because we want each instance of the struct to own all of its data, and for that data to be valid for as long as the entire struct is valid. It's also possible for structs to store references to data owned by something else, but to do so requires the use of lifetimes, a Rust feature that we'll discuss in chapter 10. Lifetimes ensure that the data referenced by a struct is valid for as long as the struct is. Let's say you try to store a reference. Let's say you try to store a reference in a struct without specifying lifetimes, like the following. This won't work. Yeah, we pass a reference and it doesn't know how long it's going to live, or needs to live rather. Expected named lifetime parameter. Interesting. In chapter 10, we'll discuss how to fix these errors so we can store references in structs. But for now, we'll fix errors like these using owned types, like string instead of references like string slice. Okay, an example program using structs. To understand when we might want to use structs, let's write a program that calculates the area of a rectangle. We'll start by using single variables, and then refactor the program until we're using structs instead. Let's make a new binary project with cargo called rectangles that will take the width and height of a rectangle specified in pixels and calculate the area of that rectangle. Shows a short program with one way of doing exactly that in our project. So we have width and height. Area is the function that we specify, and we just returned that. Cool, this code succeeds in figuring out the area of the rectangle by calling the area function with each dimension, but we can do more to make this code clear and readable. The issue with this code is evident in the signature of area. The area function is supposed to calculate the area for one rectangle, but the function we wrote has two parameters, and it's not clear anywhere in our program that the parameters are related. I mean, that's technically true. Sounds like a stretch, but I do realize that, yeah, technically, they are unrelated. It would be more readable and more manageable to group width and height together. We already discussed one way we might do that in the tuple type section of chapter 3 by using tuples. So yeah, one way we could do it is by legit just using a tuple. Fair enough. In one way, this program is better. Tuples let us add a bit of structure, but remove readability because there are no names for height and width, right? That's gonna be the thing. And destructuring a tuple just for that is just kinda whack, considering that we can instead implement a type. That's just me guessing what it's going to say later. But another way, this version is less clear. Tuples don't name their elements, so we have to index into the parts of a tuple, making our calculation less obvious. As I said, mixing up the width and height wouldn't matter for the area calculation, but if you want to draw the rectangle on the screen, it does matter. We would have to keep in mind that width is the tuple index 0 and height is the tuple index 1, meaning by using this option, we kinda like made it worse. No, I actually would absolutely argue that we just straight up made it worse. Yeah. Then, this would be even harder for someone else to figure out and keep in mind if they were to use our code, because we haven't conveyed the meaning of our data in our code. It's now easier to introduce errors. Refactoring with structs, adding more meaning. We'll use structs to add meaning by labeling the data. We can transform the tuple we're using into a struct with the name for the whole as well as names for the parts. Yes. So now we have a struct rectangle that is width and height. Love it. Very simple. Oh, actually, I think that I haven't really noticed is the fact that you don't put parentheses after the struct. It's not like you're first initiating the constructor of the struct and then setting the values. It's like, no, it's one single operation. And then we pass a reference, interestingly. Oh, because to print line. Yeah, still, why are we passing a reference? We can give... Huh? Why are we using a reference? We don't need to. We can give out the ownership. We don't need it. Right? I don't see there's any need to do this. Okay, so area, we pass an instance of rectangle, and here we go. Yeah, that's better. That's better. It's not a huge change from the first thing, but it is a bit better. I like this type of struct more than a class, and not a hotkey at the very least. Not even sure what my point is exactly, like why I like this more. I guess it's because in Rust, well, it's type strict, so you can, like, there is a reason to make a class, but in this case a struct, to be more specific for the type that you're looking for. When in auto hotkey, you can still decide to pass literally everything that you want, and like walk free after doing so. So it's simply more useful in something like Rust. Then in main, we created a particular instance of rectangle that has a width and height. Our area function is now defined with one parameter. I find it interesting that even the functions are lowercased. I don't like that, honestly. And the fact that Rust uses underscores, so snake case, like, come on, really? Like, true, I'm going to try to get used to it, but I don't particularly like it. Which we've named rectangle, whose type is an immutable borrow of a struct rectangle instance. As we want to borrow the struct rather than take ownership of it. Why? This way main retains its ownership and can continue using that rectangle, which is the reason we use the ampersand in the function signature and what we call the function. Fair enough, okay, yeah. Okay, fair enough. The area function accesses the width and height fields of the rectangle instance. Note that accessing fields of a borrowed struct instance does not move the field values, which is why you often see borrows of structs. Our function signature for area now says exactly what we mean. Calculate the area of a rectangle using its width and height fields. This conveys that the width and the height are related to each other and gives descriptive names to the values rather than using the tuple index values of 0 and 1. This is a win for clarity. True. Adding useful functionality with derived traits. Oh, already? It'd be useful to be able to print an instance of rectangle while we're debugging our program. Yes, it would be. Holy shit. And see the values for all its fields. Tries using the printline macro as we used in previous chapters. That won't work, however, because we didn't implement some sort of trait, right? When we compile this code, we get an error with this core message. Rectangle doesn't implement std format display. Interesting. The printline macro can do many things of formatting, and by default, the curly brackets tell printline to use formatting known as display. Output intended for direct end user consumption. The primitive types we've seen so far implement display by default because there's only one way you'd want to show a 1 or any other primitive type to a user. But with structs, the way printline should format the output is less clear because there are more display possibilities. Do you want commas or not? Do you want to print the curly brackets? Should all the fields be shown? Due to this ambiguity, Rust doesn't try to guess what we want, and structs don't have a provided implementation of display. To use with printline and the curly brackets placeholder. Yeah, that's very fair. If we continue reading the errors, we'll find this helpful note. The trait std format display is not implemented for rectangle. Note, in format strings you may be able to use this weird syntax, or even weirder syntax, instead. Interesting. Let's try it. The printline macro call will now look like... goddamn. Putting the specifier colon question mark inside of the curly braces tells printline we want to use an output format called debug. The debug trait enables us to print our struct in a way that is useful for developers, so we can see its value while we're debugging our code. Compile the code with this change. Drat! Well, we still get the error. Rectangle doesn't implement debug. Well. But again, the compiler gives us a helpful note. I like this, like the fact that sometimes you may be able to follow the compiler to fix the issue for you, rather than being stuck at it, not understanding what the fuck you're supposed to do. Very helpful. The trait debug is not implemented for rectangle. Add derive debug to rectangle to, or manually import debug for rectangle. Rust does include functionality to print out debugging information, but we have to explicitly opt in to make that functionality available for our struct. To do that, we add the outer attribute derive debug just before the struct definition. Okay. Now, when we run the program, we won't get any errors, and we'll see the following output. I see, that's pretty reasonable. Nice, it's not the prettiest output, but it shows the values of all the fields for this instance, which would definitely help during debugging. When we have larger structs, it's useful to have output that's a bit easier to read. In those cases, we can use this weird syntax instead of this weird syntax in the printline string. In this example, using the hella weird syntax style, we will output the following. That's very useful to have as a default, but also to make you opt into it rather than just like shoving it into you. Another way to print out a value using the debug format is to use the debug macro. Which takes ownership of an expression, as opposed to print line, which takes a reference, prints the file and line numbers of where the debug macro call occurs in your code, along with the resultant value of that expression, and returns ownership of the value. God damn. Calling the debug macro prints to the standard error console stream. As opposed to print line, which prints to the standard output console stream. We'll talk about those two streams in the later chapter. Here's an example where we're interested in the value that gets assigned to the width field as well as the value of the whole struct in rect1. So we do derive debug already. We specify it. Oh, so this will automatically print to std_err. And then it will still assign the actual value, because it returns it, onto the width, and then we can, holy shit, wow, that's so cool. We can put debug around the expression, and because debug returns ownership of the expression's value, the width field will get the same value as if we didn't have the debug call there. We don't want debug to take ownership of rect1, so we use a reference to rect1 in the next call. Here's what the output of this example looks like. Okay, so the usual thing, and then on this line in this file, this is the expression and what it evaluates to, and then on this line, this file, this evaluates to, or rather is equal to, this in pretty formatting. Wow, I love this. Right, but if you're trying to debug a struct, you have to actually give it that trait. We can see the first bit of output came from source main line 10, where we're debugging the expression of this expression, and its resultant value is 60. The debug formatting implemented for integers is to print only their value. The debug call on line 14 outputs the value of rect1, which is the rectangle struct. This output uses the pretty debug formatting of the rectangle type. The debug macro can be really helpful. Yeah, I can very much see that when you're trying to figure out what your code is doing. I love this. In addition to the debug trait, Rust has provided a number of traits for us to use with the derive attribute that can add useful behavior to our custom types. Those traits and their behaviors are listed in Appendix C. We'll cover how to implement these traits. Yawning here. No, it's not boring. And actually the opposite, like, it's becoming more and more interesting by the minute. Fog. Writing programs in this language? Goddamn. Having guarantees all over the place is just so nice. We'll cover how to implement these traits with custom behavior, as well as how to create your own traits in Chapter 10. So traits are kinda like interfaces. Not quite, but they are like interfaces in the same way that structs are kinda like classes. Yes, not quite, but the ideas somewhat correlate. There are also many attributes other than derive. For more information, see the attributes section. Okay, our area function is very specific. It only computes the area of rectangles. It would be helpful to tie this behavior more closely to our rectangle struct because it won't work with any other type. Let's look at how we can continue to refactor this code by turning the area function into an area method defined on our rectangle type. Right! Holy shit! That's cool. Methods are similar to functions when declare them using with the fn keyword and a name. They can have parameters and a return value, and they contain some code that's run when the method is called from somewhere else. Unlike functions, methods are defined within the context of a struct, or a num, or a trait object, which we cover in later chapters, respectively. No, without respect, we hate them. And their first parameter is always self. So, just like in Python, you have to be explicit about it, which represents the instance of the struct the method is being called on. Defining methods. Let's change the area function that has a rectangle instance as a parameter and instead make an area method defined on the rectangle struct. Okay, so we derive all the same. It has to be separate, which I don't quite like. The fact that instead of being inside of the struct, we instead do impl rectangle. Which is, I guess, the reason why structs still should be contained in a single file, separate from everything else. So we implement into rectangle this function that takes a reference to self and returns an integer. Okay. But there is an interesting thing. Oh wait, no. It's not like you'll be able to put impl into the main function, I feel like. You probably can't, right? I thought that you can manipulate when a method appears, when in reality, not really. To define the function within the context of rectangle, To define the function within the context of rectangle, we start an implementation block for rectangle. Everything within this impl block will be associated with the rectangle type. Then we move the area function. within the impl curly brackets and change the first. I'm having like huge deja vu right now. Like immense deja vu for some reason. It's such a strange feeling. Right. Within the impl curly brackets and change the first, and in this case only, parameter to be self and the signature, and everywhere within the body. In main, where we call the area function, and pass rect1 as an argument, we can instead use method syntax to call the area method on our rectangle instance. The method syntax goes after an instance. Yes, we add a dot followed by the method name, parentheses, or slash and any arguments. And the signature for area, right, And the signature for area, we use self instead of, yeah. The self reference, by the way, is actually short for self, for self of type self. That's strange. Within an impl block, the type self, with a capital letter, is an alias for the type that the impl block is for. Ooh, that's useful. Methods must have a parameter named self, or type self, of type self for their first parameter. So Rust lets you abbreviate this with only the name self in the first parameter spot. Note that we still need to use the ampersand in front of the self shorthand to indicate that this method borrows the self instance, just as we did in rectangle, ampersand rectangle. Methods can take ownership of self. Borrow self immutably, as we've done here, or borrow self mutably, just as they can any other parameter. That's cool. We chose ampersand self here for the same reason we used ampersand rectangle in the function version. We don't want to take ownership, and we just want to read data in the struct, not write to it. If we wanted to change the instance that we've called the method on as part of what the method does, we'd use mute self as the first parameter. So in a usual programming language, what I would maybe do is do the changes and then return this. So return the instance that is passed and overwrite. Because you don't have any way to know, or no convenient way to know whether a method / function modifies your data or not. In Rust, you can be sure, because if it does modify some data, it has to be passed as mutable. So here, making methods and functions that actually mutate data is more viable because it's so explicit. Having a method that takes ownership of the instance by using just self as the first parameter is rare. This technique is usually used when the method transforms self into something else, and you want to prevent the caller from using the original instance after the transformation. The main reason for using methods instead of functions, in addition to providing method syntax and not having to repeat the type of self in every method's signature, is for organization. We've put all the things we can do with an instance of a type in one impl block, rather than making future users of our code search for capabilities of rectangle in various places in the library that we provide. True. Note that we can choose to give a method the same name as one of the struct's fields. Oh, for example, we can define a method on a rectangle that is also named width. And then different things happen depending on whether you use brackets or not, which is interesting. It's not really something that you should be doing, to be fair. Pretty much ever, but it's cool that you can. Here we're choosing to make the width method return true if the value in the instance width field is greater than 0, and false if the value is 0. We can use a field within a method, and by the way, that is done automatically for us because the type of both width and height is an unsigned integer, meaning they cannot be negative. We can use a field within a method of the same name for any purpose. In main, when we follow rect1 with parentheses, Rust knows we mean the method width. When we don't use parentheses, Rust knows we mean the field width. Often, but not always, when we give a method the same name as a field, we want it to only return the value in the field and do nothing else. Methods like this are called getters, and Rust does not implement them automatically for struct fields, as some other languages do. Really? Hold up. But isn't a getter is just like dot notation in this case? Getters are useful because you can make the field private, but the method public. And thus enable read-only access to that field as part of the types public API. We will discuss what public and private are and how to designate a field or method as public or private. That's good to know that that is a thing, because I was worrying that, wait, is there like no private in Rust? Supposedly you can. Good to know. Where's the this operator? If you're calling the method on a pointer to the object and need to dereference the pointer first. Interesting. In other words, if object is a pointer, object arrow something is similar to this. Oh wow, huh. Rust doesn't have an equivalent to that operator. Instead, Rust has a feature called automatic referencing and gereferencing. Calling methods is one of the few places in Rust that has this behavior. Here's how it works. When you call a method with object something, Rust automatically adds in the ampersand mute, or asterisk, so object, in that case P1, matches the signature of the method. Oh, because self can be different, and having to keep track of that is kind of annoying, so Rust does it for you. In other words, the following are the same. That's cool. The first one looks much cleaner. This automatic referencing behavior works because methods have a clear receiver, the type of self. Given the receiver and name of a method, Rust can figure out definitively whether the method is reading ampersand self, mutating, or consuming. The fact that Rust makes borrowing implicit for method receivers is a big part of making ownership ergonomic in practice. Well, putting ampersands all over the place isn't necessarily ergonomic. Overall, I do understand the complaints some people have that Rust syntax is ugly. Yeah, I can see that. But while it is ugly, it also makes a lot of sense to me, where like pretty much everything I'm okay with. Methods with more parameters. Let's practice using methods by implementing a second method on the rectangle struct. This time we want an instance of rectangle to take another instance of rectangle and return true if the second rectangle can fit completely within self, the first rectangle. Otherwise it should return false. That is, once we've defined the canHold method, we want to be able to write the program shown in there. Interesting. The expected output would look like the following. Because both dimensions of rect2 are smaller than the dimensions of rect1, but rect3 is wider than rect1. We know we want to define a method, so it will be within the impl rectangle block. The method name can be canHold, and it will take an immutable borrow of another rectangle as a parameter. We can tell what the type of the parameter will be. by looking at the code that calls the method. Passes in ampersand that, which is an immutable borrow, to rect2, an instance of rectangle. This makes sense because we only need to read rect2 rather than write, which would mean we'd need a mutable borrow, and we want main to retain ownership of rect2, so we can use it again after calling the canHold method. The return value of canHold will be a boolean, and the implementation will check whether the width and height of self are greater than the width and height of another rectangle, respectively. Let's add the new canHold method to the impl block there. Okay, so how is it going to work? So we have area canHold, we pass self and another rectangle called other, interestingly. So self width is bigger than that, and we use the AND operator, and we just return this expression. Yeah, that's quite simple. When we run this code with the main function, we'll get our desired output. Methods can take multiple parameters that we add to the signature after the self parameter, and those parameters will work just like parameters in functions. Associated functions. All functions defined within an impl block are called associated functions because they're associated with the type named after the impl. We can define associated functions that don't have self as their first parameter, and thus are not methods because they don't need an instance of the type to work with. Interesting. We already used one function like this, the string from function that's defined on the string type. Associated functions that aren't methods are often used for constructors that will return a new instance of the struct. These are often called new, but new isn't a special name and isn't built into the language. For example, we could choose to provide an associated function named square that would only have one dimension parameter. So there is technically constructor overloading. Not quite, because you have to use different names, but kinda. Well, this is more similar to builders, I guess. Yeah. For example, we could choose to provide an associated function named square, and it would have one dimension parameter and use that as both width and height, thus making it easier to create a square rectangle rather than having to specify the same value twice. And we can just use self as a type instead of repeating rectangle, where we only now have to use it once in the impl line, and all the following times we just use self. Meaning if we ever change the name of this struct, we will have to change it in less places. The self keywords in the return type, yes, and the return type and in the body of the function are aliases for the type that appears after the impl keyword, which in this case is rectangle. To call this associated function, we use the double colon syntax with the struct name. I see. So that's the difference. So they're kinda like static methods in, say, AutoHotkey. Yeah, that correlation makes it easier to understand. This function is namespaced by the struct. The double colon syntax is used for both associated functions and namespaces created by modules. We'll discuss modules in there. Multiple impl blocks. Each struct is allowed to have multiple impl blocks. Why? For example, is equivalent to code there, which has each method in its own impl block. Right, but my question is, why would you do this? There is no yeah, as I said, to separate these methods into multiple impl blocks here, but this is valid syntax. We'll see a case in which multiple impl blocks are useful in a later chapter where we discuss generic types and traits. Summary. Structs lets you create custom types that are meaningful for your domain. By using structs, you can keep associated pieces of data connected to each other and name each piece to make your code clear. In impl blocks, you can define functions that are associated with your type, and methods are a kind of associated function that lets you specify the behavior that instances of your structs have. But structs aren't the only way you can create custom types. Let's turn to Rust's enum feature to add another tool to your toolbox. Enums have a lot of hype and more lower level languages, like C for example. In this chapter, we'll look at enumerations, also referred to as enums. Enums allow you to define a type by enumerating its possible variants. That's an interesting way to look at it. First, we'll define and use an enum to show how an enum can encode meaning along with data. Next, we'll explore a particularly useful enum called option, which expresses that a value can either be something or nothing. Then we'll look at how pattern matching in the match expression makes it easy to run different code for different values of an enum. Finally, we'll cover how the if-let construct is another convenient and concise idiom available to handle enums in your code. Defining an enum, where structs give you a way of grouping together related fields and data, like a rectangle with its width and height, enums gives you a way of saying a value is one of the possible set of values. For example, we may want to say that rectangle is one of a set of possible shapes that also includes circle and triangle. To do this, Rust allows us to encode these possibilities as an enum. Let's look at a situation we might want to express in code and see why enums are useful and more appropriate than structs in this case. Say we need to work with IP addresses. Currently, two major standards are used for IP addresses, version 4 and version 6. Because these are the only possibilities for an IP address that our program will come across, we can enumerate all possible variants, which is where enumeration gets its name. Any IP address can either be a version 4 or a version 6 address, but not both at the same time. That property of IP addresses makes the enum data structure appropriate, because an enum value can only be one of its variants. Both version 4 and version 6 addresses are still fundamentally IP addresses, so they should be treated as the same type when the code is handling situations that apply to any kind of IP address. We can express this concept in code by defining an IP address kind enumeration and listing the possible kinds an IP address can be, v4 and v6. So we literally just list them. These are the variants of the enum. IP address kind is now a custom data type that we can use somewhere in our code. I wonder how we do that. Enum values. We can create instances of each of the two variants of this enum like this. So we get the enum type. Note that the variants of the enum are namespaced under its identifier, and we use a double colon to separate the two. This is useful because now both values of this and this are the same type, this. We can then, for instance, define a function that takes any IP address. But that is specifically the kind. You don't set like the actual value to it because the value is the type. And we can call this function with either variant. Using enums has even more advantages. Thinking more about our IP address type, at the moment we don't have a way to store the actual IP address data. We only know what kind it is. Yeah. Given that you just learned about structs in chapter 5, you might be tempted to tackle this problem with structs. Like this. Yes, I am indeed tempted. Here we've defined a struct IP address that has two fields, a kind field that is of type IP address kind, the enum we defined previously, and an address field of type string. We have two instances. We have two instances of this struct. The first is home and has the value of 4 as its kind with associated address data of this. The second instance is loopback, has the other variant of that kind, which is 6, and an address which is pretty weird, by the way, double colon 1 associated with it. We've used the struct to bundle the kind and addressed values together, so now the variant is associated with the value. However, representing the same concept using just an enum is more concise, so we can do that. Oh! Rather than an enum inside a struct, you can put data directly into each enum's variant. That's brilliant. This new definition of the IP address enum says that both v4 and v6 variants will have associated string values. That's pretty cool. So we implement the type, then the type of that type, and then its value. We attach data to each variant of the enum directly, so there is no need for an extra struct. Here, it's also easier to see another detail of how enums work. The name of each enum variant that we define also becomes a function that constructs an instance of the num, so they kind of become constructors. That is, this is a function that calls a function call that takes a string argument and returns an instance to the IP address type. We automatically get this constructor function defined as a result of defining the enum. There's another advantage to using an enum rather than a struct. Each variant can have different types and amounts of associated data. Version 4 IP addresses will always have 4 numeric components and will have values between 0 and 255. If you wanted to store v4 addresses as 4 U8 values but still express v6 addresses as one string value, we wouldn't be able to with a struct. Enums handle this case with ease. Oh wow! That's so incredibly nice. Holy shit. We've shown several different ways to define data structures to store version 4 and version 6 IP addresses. However, as it turns out, wanting to store IP addresses and encode which kind they are is so common that the standard library has a definition we can use. Lol. We can look at how the standard library defines IP address. It has the exact enum and variants that we've defined and used, but it embeds the address data inside the variants in the form of two different structs, which are defined differently for each variant. I really like how it says snip, like that's so cute. So struct this address and this address, and that may then also have method, which is why it's a struct, I imagine. And you just put the type there, so now it's an enum of structs instead of the other way around. This code illustrates that you can put any kind of data inside an enum variant. Strings, numeric types, or structs, for example. You can even include another enum. Also, standard library types are often not much more complicated than what you might come up with. Note that even though the standard library contains a definition for IP address, we can still create and use our own definition. That's pretty cool, without conflict, because we haven't brought the standard library's definition into scope. We'll talk more about bringing types into scope in Chapter 7. Let's look at another example of an enum and listing of this. This one has a wide variety of types embedded in its variants. So message is quit, move, that we actually may name the values of, which is interesting, write, and change color. What do you mean message move? That I don't get. This enum has 4 variants with different types. Quit has no data associated with it at all. Move has named fields, like a struct does. Write includes a single string. Change color includes 3 I32 values. Should they even be I32? I think the cool thing about strongly typed languages, is the fact that you can be hyper-specific. So if change color accepts RGB, meaning red, green, blue, then you should use unsigned 8. And now change color immediately becomes more understandable in what it expects. And also, by using more limiting types that have less memory, you restrict from setting different values. Defining an enum with variants such as the ones in listing 6.2 is similar to defining different kinds of struct definitions. Except the enum doesn't use the struct keyword, and all the variants are grouped together under the message type. The following structs could hold the same data, but the preceding enum variants hold. So unit struct. Right, so we could use the struct instead, but the positive of an enum is that we hold these values, which are types by themselves, all together. Fuck, this is so interesting. But if we use the different structs, each of which has its own type, we couldn't as easily define a function to take any of these kinds of messages as we could with the message enum defined in there, which is a single type. there is one more similarity between enums and structs. Just as we are able to define methods on structs using impl. Oh, I see. We're also able to define methods on enums. Here's the method named call that we could define on our message enum. So message write, we put a string into there. So now we have the instance of this enum, which we now can call. Self being the value, rather, not the instance. It has a type, but the instance is the value, I think. Yeah. I guess doing this, like, you would do this for the type. Alright. I am tired. As you maybe have noticed, by how I was reading it all. So I'm gonna replace this link with this new one and continue maybe tomorrow. Probably tomorrow. As I've explained already, I don't have much to do other than do the course, learn Rust, or watch Hunter x Hunter right now. So you'll probably see another stream tomorrow. Thank you for watching, everyone, and I'm going to be ending stream. Goodbye.